Math 1343, Week 10, Video 2. What is analysis of variance? ANOVA, if you will. Most of the time, I will call it precisely that. ANOVA, analysis of variance. But what is it, and what is its goal? Well, both of those questions are pretty easy to answer. Analysis of variance is just a hypothesis test. So like all the hypothesis tests we've seen in the past, we have two choices, critical value approach or p-value approach. But regardless of our choice, we're going to go through the same steps. Number one, state the hypotheses. Number two, if we're doing the critical value approach, determine the critical value and rejection and non-rejection regions. Number three, calculate the test statistic. Number four, make a decision about the null hypothesis. And then finally, five, answer the question in the context of the problem. But if we're doing the p-value approach, then it is state the hypotheses, calculate the test statistic, calculate the p-value, which is the area of the tail cut off by the test statistic, make a decision based on whether or not the p-value is larger or smaller than the significance level, and then answer your question. But if we're going to perform a hypothesis test, then what exactly are we testing? What is the goal of an analysis of variance test? The goal of an analysis of a variance test is to test multiple population means for equality, simultaneously. There we go. Think of it this way. When we did a goodness of fit test and in a roundabout sort of way, a test for association, we were testing multiple population proportions simultaneously, especially in the goodness of fit test, where there was a claim about multiple population proportions. That was the null hypothesis, and the alternative hypothesis was at least one of these claims is wrong. Analysis of variance is kind of like the mean equivalent of that, meaning that we're going to test multiple populations simultaneously, but we're always going to be testing the same thing. Do all of these populations have the same mean, or do they not? Now, an analysis of variance test, and it's bothering me that I didn't capitalize V there, an analysis of variance test will only answer the question, are they all equal, or do we have statistically significant data that suggests at least two of them are different? Because they could all be equal except one guy. What it doesn't tell us is, okay, if they're not equal, which one is the guilty party, or is there more than one? We can do some post-ANOVA analysis to answer that question, which will be the next series of videos. But for now, that's the goal of an analysis of variance test. Its goal is to test multiple population means for equality simultaneously. I'm going to show you an example of what I'm talking about. I've put together some data that I extracted from the Major League Baseball statistics archive, if you will. And I've pulled a lot of data by copying and pasting into Excel and formatting it nicely. Data measuring hits by batting position per team for Major League Baseball's 2019 regular season. There's the website that I extracted it from. If you're not familiar with baseball, that's okay. All you need to know right now is that there are 9 positions in the batting order, and when you're up to bat, you can get a hit. So what do we have here? Well, in each column, we have the number of hits obtained for all the different teams in Major League Baseball in the year 2019. For example, from the first batting position, the guy who was up first, in one team over the course of the season, there was 186 hits from the first batting position. In another team, there was 215. In another team, there was 194, all the way down to all 30 teams in Major League Baseball. And here's the number of hits that were gotten by people who batted in the second position on all 30 teams. And then from third position, fourth position, all the way down to the end of the batting order in ninth position. And to the right over here, we have some summary statistics for each of these populations, the population of batters in the first position, second, third, et cetera, et cetera. Now, each of these has a sample size of 30 because there are 30 teams in Major League Baseball as of this data set. For people batting from the first position, the mean number of hits obtained per team was 181.33, with a standard deviation of 17.82. In the second batting position, of which there were 30 data points in the sample because there's 30 teams, the mean number of hits was 179.73 per team, with a standard deviation of this. If it looks like my eyes are always going off to the side, it's because the little video here, which I just moved to the middle, is off to the side. But maybe if I put it here, I won't always look like I'm looking off to the side. But anyway, for each of the batting positions, we have some summary statistics, and I meant to title this summary statistics. So let's do that real quick. As I want to, we'll center that. All right, so what could we possibly be asking here? We could be asking, is the mean number of hits the same based on batting position? For example, the mean number of hits from the first position is 181.33. But if you go to the ninth position, the last in the batting order, it's only 113.13. Now, this is probably by design. I'm not an expert on setting up batting orders, but I imagine that the team captains probably want to put their stronger players up front. Because if you notice, there is a trend that these numbers do slowly decrease as we go through the batting order. But the question we're going to attempt to answer is this data significant enough to claim that some of these means might be different, or is there differences just based on the sample that we took? But when I say sample, I mean the sample from the 2019 season, where the population is all seasons of baseball ever played. And what do these standard deviations have to do with that? So that's our goal. Our goal is to test multiple population means simultaneously. So if we were starting the ANOVA test for this example, then we could go ahead and state our hypotheses. Our null hypothesis, why are we not drawing? There we go. Our null hypothesis would be the mean number of hits, is the same for each spot in the batting order. Let's erase that. Still erasing. Here we go. For each spot in the batting order. And we could also write this in terms of mu's. We could say mu1 for the mean number of hits from the first position is equal to mu2 is equal to, and then we could use some ellipses and go all the way to mu9. So if that was our null hypothesis, then what would our alternative hypothesis be? Our alternative hypothesis would be at least two of the means are different. And we could put that in the context of the problem. But from a generic perspective, you can say that your alternative is always at least two of the means are different. And I knew this was going to happen at some point in the semester. Up until now, I've always used HA for the alternative hypothesis. But I think I warned you at the beginning of this class that sometimes I'm going to put H1 because that's the notation that was used in the book that I used prior to the one that I'm currently using. So generically speaking, you can say that the null hypothesis for an ANOVA test is always the means are all equal. And the alternative is at least two of them are different. All right, I think that wraps up this video. Before we get into the nitty-gritty of how to do the hypothesis test, I'm going to show you a little bit more of a visual argument of what we're attempting to do in the next video. And that will wrap up this video.